Confidence intervals. Let's review the sampling distribution of the sample proportion. A sampling distribution describes how values of a statistic vary from sample to sample. A normal distribution may result under certain conditions. The conditions are that a representative random sample is collected, n times p needs to be 10 or more, and n times 1 minus p also needs to be 10 or more. Consider the central or middle 95% of z-values. So let's sketch the standard normal curve and find where that middle 95% of values is located. So here is our distribution with the symmetric mound-shaped curve with the mean of 0, and the middle 95% will fall somewhere between the two marks indicated. Now 2.5% of z-scores will be less than that left point, and 97.5%, the 95% in the middle plus the 2.5% on the left, would be less than that right endpoint. We can label the percentages, so 2.5% is on the left, 95% is bound in the middle, and another 2.5% is to the right of the location. It turns out that those values are negative 1.96 and positive 1.96. How does this inform us about the middle 95% of sample proportion values? So we have the same curve drawn, the symmetric bell curve or normal curve, mean 0, and we have our negative 1.96 and positive 1.96 locations marked. Notice the breakdown of percentages is the same as in the previous slide. And on the z-scale, our locations would be at negative 1.96 and positive 1.96. In terms of proportions, negative 1.96 in terms of a z-score just means the original value is 1.96 standard deviations below the mean. So if we take the mean, mu sub p hat, subtract 1.96 times the standard deviation of p hat, that would be the location on the proportion scale. Notice the right endpoint would be the same distance, just above instead of below, and then we know what about the distance from the mean, which on the z-scale is 0, or mu sub p hat, or p, in terms of the proportion scale, out to, and we'll just choose the right endpoint. Well, what do we know about that distance? Well, how far did we move from the mean? We moved 1.96 times sigma sub p hat. So that is the distance from the mean out to that right endpoint. What do you know is true about 95% of sample proportion values based on what we have just discovered? Well, if the mean to that right endpoint is 1.96 times sigma sub p hat, let's consider a sample proportion. Suppose we get a p hat value somewhere between 0 and negative 1. Well, if we add that distance, 1.96 sigma sub p hat, on both sides of that location. So first let's subtract, and we'll get a left edge or a left endpoint. The next thing we want to do is, starting over at p hat, go to the right, or add that same distance, and we get a right endpoint. Well, what do you know about that interval? So from the left endpoint to the right endpoint we've just constructed, what is contained in that interval? the value of P, or the mean of the sampling distribution, is located in that interval. And this would work in 95% of sample proportion values. Let's consider an example. Suppose 25% of residents are Hispanic. So the mean of all sample proportions, mu sub p hat, equals whatever the rate or the prevalence is in the population. So that would be 25% written as a decimal, or 0.25. Now consider a random sample of n equal to 200 residents. What do we know about the sampling distribution of p hat if we look at the sample proportion out of 200 at a time who are Hispanic? Well, the mean is going to be mu sub p hat equals p, which equals 0.25. Now the standard deviation is sigma sub p hat, and that is simply the square root of p times 1 minus p over n, which in this case calculates out to be about 0.03. And we will round this just to 2 digits just for simplicity. Normally we would keep more digits. What about the shape? Well, it is approximately normal in distribution. Why? Because we had a random sample. N times P would be 200 times 0.25, and that equals 50. So that meets my at least 10 requirement. And N times 1 minus P would be 200 times 0.75, which is 150, and that also exceeds 10. So 95% of sample proportion values lie between what? The mean value minus that z-score for 95% confidence of 1.96 times the standard deviation, which remember we rounded off to 0.03. So that is 0.1912 when we round to 4 digits. Similarly, the right endpoint would be the mean 0.25 plus z 1.96 times the standard deviation 0.03, and that gives me a right edge of 0.3088. Now suppose 25% of residents are Hispanic, but you don't know this. Consider a random sample of n equal to 200 residents. Estimate P if there are 44 Hispanics among the sample of 200 residents. What would we do? Well, let's calculate the sample proportion. So P hat is 44 over 200, which equals 0.22, and that is exact. Now what we want to do is add and then subtract the estimated standard deviation if we had that. So what we're going to do is, since we don't know the value of P, we're going to substitute the value of P hat in its place. So we say S sub P hat, which is the estimated standard deviation, is the square root of P hat times 1 minus P hat over n. So in this case, that is going to be the square root of 0.22 times 1 minus 0.22, which is the 0.78, divided by the sample size of 200. That turns out to be 0.029292. So for 95% confidence, start with your point estimate, 0.22, minus the z-score, 1.96, times the standard deviation, 0.029292, and that gives you a lower limit of 0.1626, and then 0.25 plus 1.96 times 0.029292 equals 0.2774. So the formula to estimate the parameter P, the population proportion, when the conditions are met, so you want to make sure that it's valid to do this, would be, for the lower limit, p hat minus z times the square root of p hat times 1 minus p hat divided by n. The upper limit really is the same thing, just with a plus. So you're adding p hat plus z times the square root of p hat times 1 minus p hat divided by n. Now the summary of findings can be formatted as follows. With 95% confidence, the proportion of all residents who are Hispanic is between 0.1626 and 0.2774. Another way to state this is to convert the proportions to percentages and say, with 95% confidence, 16.26% to 27.74% of all residents are Hispanic. Notice in the summary, we are extending what we found to the population of all residents. Now we discussed the z-score for what is called 95% confidence. The same derivation can be used for different levels of confidence. We are going to look at a few commonly used levels of confidence and their corresponding z-scores. The chart below will give you the level of confidence and the z-score to use to bound that portion of z-scores. This would be the z-value to use when you're estimating a proportion using the confidence interval. Common confidence levels include 90%, 95%, 96%, 98%, and 99%. The corresponding z-scores are 1.645 for 90% confidence, the 1.96 or 1.960 we found for 95%, 2.054 for 96% confidence, 2.326 for 98% confidence, and finally 2.576 for 99% confidence. You need to make sure you write these scores down either on a separate piece of paper, or you can copy these onto your z-table, your normal table, so that you have those for tests and quizzes. So let's review the steps in estimation. When you are asked to estimate a population proportion, calculate the sample proportion, p hat. Locate the z-score based on the level of confidence. Using the sample size, n, the sample proportion, p hat, and the z-score, calculate the lower limit and the upper limit. Be sure to provide an interpretation or a summary of your interval in context of the scenario. And finally, if asked, verify the interval is valid. This means you need a random representative sample that was collected. N times p hat needs to be 10 or more, and n times 1 minus p hat needs to be 10 or more.